Good morning, lovely 13s. Right, buddies, today we are going to keep rocking on in our momentum unit, which I think is quite exciting. It's a tricky unit, this, and now we're going to the heavy lifting section. This actually finishes the unit, but it's quite cool, though, so here you go. Title for today, my buddies, is The Coefficient of Restitution. Cool, cool, cool. So put that down. Now, essentially, buddies, you'll know from in real life, like being in PE and stuff like that, and maybe you actually like to do sports of your own accord as well, not just PE. But if you were to drop a ball, for instance, like a basketball, it doesn't actually bounce back up to your hand height. It doesn't get, well, in the case of a basketball, it doesn't get anywhere near your hand height. You have to actually push down on it to kind of make it dribble. And the same with the tennis ball, too. Like you got to throw the ball into the ground to make it come back up to your hand height. The reason for that is kinetic energy is lost in the collision between the ball and the ground. Now, kinetic energy, well, because like work will be done and resistances happen and sound happens and there's compression in the ball and there's lots of reasons why energy is lost to the system when a ball bounces off the ground. Cool. So it's not just balls that do that though, it's kind of any collision has kind of energy loss in it. And so here's what we've got. We've got the coefficient of restitution, which I think is called Newton's law of impact as well. I'm not all the way sure on that, so don't quote me, but yeah, here we go. Here's what you've got, buddies. You've got E equals V sap over V ap. Now I'm going to just try to explain to you what each of these things are. It's just a simple formula, and here we go. V ap is the approach speed. Okay, so get that labeled. So it's how quick that two objects are approaching one another. If it was a ball heading toward the ground, it would just be the speed that the ball heads toward the ground. It wouldn't have a second object. It's just its own speed, really. And VSAP is the separation speed. It's how far, or it's how quick they bounce off of each other. Yeah, so say you dropped a ball toward the ground at 5 meters per second, it might bounce up at 3 meters per second. That's kind of what I'm getting at here. And E, my lovelies, lowercase e, same as the E that we use in regular maths, is the coefficient of restitution, okay? It's unitless, because just like have a look, it's just a ratio of speeds, okay? So it just represents a ratio, which means it wouldn't have a unit. Cool, cool, cool. Now, E is always between 0 and 1, inclusive of 0, but not inclusive of 1. Can you think of why that might be? Why would it be that E is between 0 and 1? Well, just think of it this way here. I'm just going to tell you, because I'm not in the room, so I have to just tell you. So, here's what it is. If E, were to equal 1, it would mean that the separation speed equaled the approach speed, which would mean that if you drop the tennis ball, it would bounce back up exactly to your hand, so no energy would be lost at all. So that's kind of the best case, ideal, perfect solution, that it would come right back up to the exact same height. E couldn't be more than 1, because then it would be like that movie Flubber, that you would drop the ball and then all of a sudden it would like bounce all the way up to the ceiling or bounce into outer space and stuff, and that's just not how the real world works, and so E has to be less than 1. It can be all the way to 0, because that would mean that the thing just kind of fused with the ground. Say if you were dropping a brick into sand, like you might get a 0 there. So that's what you've got, my buddies. So I just wanted to show you a couple of examples of how this would work in a really easy way first. So pictures are super helpful, just like lots of stuff in mechanics. The pictures are really helpful. And here you go. Here's a picture of a ball bouncing on the floor. So it goes toward the floor at 10 meters per second, it bounces off the floor at 8 meters per second. Just to use the formula in the simplest possible way, here we go. What is E? What's the coefficient of restitution? Well, E is going to equal this. It's the separation, the separation speed, so the final speed of 8, over the approach speed, which is the initial speed of 10. Bish bash bosh, that's what you've got. The gap is closing at 10 meters per second, then it's leaving at 8 meters per second. E is equal to 0.8. Cool beans, 80% of the speed is retained through the collision. Cool. One more, here we go. Here we go. This is a little bit more complicated. It's not really too bad though. Here we go. We've got a before and an after. So in the before, we're dealing with the approach speed. Cool, V app. Well, the approach speed here, you have to pick a direction to be positive. So let's go oh, no, you don't. Here, let's just cut it. It's 8. Okay, it's 8, my lovelies. It's 8 meters per second because the gap is closing at 8 meters per second. Cool beans? Cool. The separation speed, what are we going to get there? The separation speed then, after they go off of each other, well, when they're going off of each other, then what's kind of the difference in speed there? Well, what are we going to get? The after speeds. Well, once they're bouncing off of each other, the after speed, my lovelies, is just going to be 4 meters per second, and that means that we're going to be having an E of separation, which is 4 over 8, which is 0.5. So hopefully not too bad on that. There's more technical ones, which are actually easier to explain than the simple ones I always find, coming up soon. So, this isn't super important, but I know in the old spec they kind of banged on about kind of conditions for collisions to occur. I don't have every single possible collision written down, but I just wanted to show you the weird examples. So here's a before picture, okay? There's a mass of A and an initial speed, so it's a U because it's initial, moving toward the right. And the same with MB and UB, both moving toward the right. For them to collide, what's the necessary condition? If they're actually going to have a collision, what has to happen? Well, yeah, you're right. The A has to be faster than B. Yeah, UA is bigger than UB. Now, after the collision, what could possibly happen? If these two guys, so mass A and mass B, both end up going toward the right, so they've smashed into each other. This would be kind of like a pool ball, or whatever we call it in English. What are they called? Billiard balls? Snooker balls. You call them snooker balls, I think. Snooker ball. If you had one of them hitting another one, the cue ball would kind of continue to move slowly in the same direction as the ball it hit. So the condition we've got here for after collision is that B better be going faster than A. Otherwise, A would be like a ghost moving through B, which is, yeah, that's important as well. Cool. This one here, it can bounce in opposite directions. In that case, it doesn't matter which one's bigger because they're just separating from each other. And the final thing that we've got is they could go together. They could coalesce, my lovelies, which is probably what I wrote there. Yes, it is. They could get stuck together and they could move off to the right. That wouldn't happen on a snooker table, but that might happen if you were very unlucky in your car and smashed into another car. That could happen that they get attached, so that's it. The only thing that's really important in all of this is what happens in these after speeds, okay? Because the approach speed is generally quite easy to work out. The approach speed here in the first one would just be UB take UA, because that would give you the UA take UB, I should say, because it would give you just kind of the speed at which the gap is closing, and UA has to be bigger than UB. Now, here you go. For the ending one, though, this is the main thing. It's just VB takes VA. Okay, so that tells you how quick that they are separating at the end in all cases. It is a vector quantity, momentum is, and speed is, or speed isn't, but velocity is. And so, yeah, you do have to define a direction to be positive, which we will see now. Cool! Here we go, buddies. It says this, our first ever real question. How exciting, buddies. Cool, 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 cool. It says a direct collision takes place between two snooker balls. Yeah! I don't need to highlight that. I don't know why I did. Okay, the white cue ball is traveling at 2 meters per second, and it hits a stationary red ball. After the collision, the red ball moves in the same direction as the cue ball was moving before the collision. The balls have equal mass, and the coefficient of restitution between the two is 0.6. Predict the velocity of the balls after the collision. So we're after the velocities after the collision. So we're after a vector quantity, we're after that. Cool. Here is what I would say, buddies. Just like every single question, it will benefit from having a little, just sneaky, cheeky, quick picture. So you ready? Here we go. Before. Well, what have we got before? Well, what we've got, first of all, is we have got, what was it, a white cue ball. So we have the white cue ball. Here it is. It said it was the same mass as the other one. So, oh well, mass of the white ball. And it's got an initial speed coming in. Its initial speed is 2 meters per second. It's hitting the red ball, so there's the mass of the red ball, but the red ball doesn't have any speed to start with because it's just sat there. Cool, so that's what we've got. After. Well, after, it says that what happens is, after the collision, the red ball moves in the same direction that the cue ball was moving before the collision. So here we go. The red ball then is going to end up moving along this way. So there's the mass of the red ball. We don't know what it is. So there's VR, not UR, the velocity of the red ball. And there's also the white ball. So it's the mass of the white ball. And the thing is, we can kind of predict. I would think it would go to the right. If I was to have a guess, I would say that the velocity of the white ball will go to the right. But if I get it wrong, if I was wrong and it actually like ricocheted off it and went the other way, I'll find out because I'll get a negative answer because of my sign convention. So that's kind of where we're at, okay? With that, does that make sense? That it doesn't matter if I get the wrong guess in there. I would presume they both move to the right. That's what I would think from having played pool before. So yeah, that's it. So for step one, my buddies, define a direction to be positive. Let's have right as positive. So, oh yeah. And here we go. I want to get the coefficient of restitution stuff out early. So here we go. E is equal to V sep over V app. Okay. Now it says in the question that the what am I on about? The ball's equal, blah, 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 blah. Oh yeah, okay, yeah. It says in the question that the E is 0.6, okay? So that's the like fraction of the velocity that is maintained through the collision. So it's 0.6. Now here's what we've got, the V sep. We don't know that one yet, V sep, so we'll leave that one in. And underneath that we'll have V app, which is the approach speed. Well, what is the approach speed based on initially? In the before pictures when we're on about the approach. How quick do they go toward each other? That's right, it's 2, buddies! So here we go, that means that 1.2 equals the separation speed. Now, that's no good, because our final answer, we actually want the velocities, so the separation speed, I hope you would agree with me, is just this. It's going to be VR, take VW, because VR has to be more. Otherwise, the VW, this back ball would ghost on through the other one like a ghost. So yeah, it's got to be bigger. So it's VR take VW. That's universally true. Even if it bounced off of each other, it would still be VR take VW because of the sign convention I have to the right. So that's all we've got there. So you might be thinking to yourself, oh good, I've got this far, but oh drat, I still can't know what VR or VW is. Darn, 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 I have no way of solving this question. Unless, buddies, you remember that momentum is always conserved. Okay? So a momentum's always conserved, and actually we're going to account for the loss of energy using the second equation. So here we go, let's do it. The momentum before. Well, I have right as positive. Don't forget, we need that sign convention going. I have right as positive. So what have we got moving to the right initially? Well, we've got MW, the white ball, moving at a speed of 2. So that's our initial momentum only. Now after, we have 2 things moving to the right, so I think, I might have it wrong, but a negative will come out. But I think I have 2 things moving to the right, and that's going to be the white ball, which is going to be MW, with the speed of VW, plus I'm going to have the red ball as well. So it's MR with a speed of VR. Now, there was something super important, and I wanted to label them MW and MR and stuff to make it more useful to you guys, to make it easier to see that which one was the white one and which one was the red one, but it says something really important. It said they were the same mass somewhere. The balls have equal mass, okay? Which means, buddies, all of the M's are the same, which means we can go on a wicked awesome scratching out party. So let's do it, buddies. So all the M's are the same. Gone, gone, gone. Which means that this here is just going to be this. It's going to be 2 equals V, W, the white ball, plus the final speed also of the red ball. And that's as far as we got. So drat, we're completely scuppered here, my lovelies. We have 2 equations and neither one of us gives the answer. Unless, oh my lovelies, it is the simultaneous equation time. And not only that, it's a really easy one. We don't even need to make the subjects messed about. Notice that this VW is negative and this VW is positive. Why don't we do 1 plus 2? Let's do it. 1 plus 2. Then that way, buddies, on the left, we've got 3.2 when you add them together. On the right, there's two lots of the VR, so it's 2VR, and then VW and the other negative VW cancel out, which means that their speed, the VR, the final speed of the red ball, is just 1.6 meters per second. It's positive, it's right. Cool beans, my buddies. Our sign you don't really need that right, but yeah, anyway. Beautiful. It's gonna be, our sign convention has worked out, okay? So it is right, like we'd expected it to be. Cool. Just to get the other one, what are we gonna do? You guys know this. Just bust it into whatever one you want. Let's go into question 1 again, into equation 1, and then we'll get 1.2 equals 1.6. Take VW to this side, 1.2 to that side, VW is equal to 1.4. It is positive meters per second, which means there's no errors in my sign convention. I didn't get a negative number out. It happened just like I asserted it would by saying right was positive, and by putting that as positive, I didn't get any negatives out. Boom, there's your final answer. So I hope that that's okay, buddies. Does that make sense? I hope. You just get the E thing out of the way first, and then you do regular conservation of momentum. Cool? Hard one time? Yeah, go on then. This is going to take ages. I'll do my very best to get through this one as quick as I can, but it takes a bit. I'm sorry. Okay, here we go. It says, an object A has mass m and speed 2u. It hits object B of mass 2m and speed u, but it's in the opposite direction to A. Okay. Now, it says the coefficient of restitution is E, okay? Now, that's all it says. Now, this is a funny old question. That's why I wanted to do it. I was going to skip this one, but it's just, I'm quite interested in doing part 2, and I thought it was funny because it gets a bit languagey. Show that the ratio of the speeds, okay, speeds, remains unchanged, whatever the value of E, okay? Speeds, buddies, don't have directions. Velocities do. So we just want to talk about the speeds. So we want to see the ratio of the speeds coming in as well as the ratio of the speeds coming out, okay? So here we go. What are we going to do first? Well, let's draw a picture. We could always benefit from that. So here we go, before. Okay. Now we've got A moving at speed 2u and B moving at that in the opposite direction to A. So here we go. For object A, it's going to be like this. Here's A. It's got speed, or it's got mass, I should say, m, and it moves with speed 2u in this way. So 2 lots of the initial speed it's got. Now B is going to be coming at it opposite in directions. So it's got mass 2m, so B's bigger, and it's coming at this one with speed u. They've got the same momentum though, that's interesting. With u in opposite direction to A, beautiful. Okay, good. That's the before. After. Okay, after. Let's have a check. We're gonna have A, we're gonna have B again, and here we go. Afterward, the coefficient of restitution is E. Okay, it doesn't tell us anything about the directions afterward, does it? Okay. I'm going to treat them like snooker balls again, and I'm going to presume that they both go right, okay? Because if I have that wrong, I'll get a negative answer out, which is cool. It just meant that they bounced off of each other, and that, if that were the case. So here we go. Let's have A again. So afterward, I'm going to have A still cruising along. So A has got mass of m, and it's going to have a speed not of 2u anymore, but it's going to be VA, the speed of A. And this guy here, B, is going to be here. It's going to have a, no, I made a mistake already. It's 2m, because it's twice as big, it said. So we have 2m here, and it's going to have VB. Cool, where VB would have to be bigger than VA if I'm right in this, if I'm right in all of this, okay? So here we go, buddies. We need a direction to be positive. I'm going to have right, okay? Right is positive. Now, because this question is weird and bizarre, it's on the ratio of the speeds. I think that what they mean is initially to finally. So let's do initial speeds in terms of the ratio. in the initial speeds, and it's just speeds, don't forget, not velocities, so it doesn't matter that b is moving to the left in my picture. Here we go, the initial speeds, a to b, because it wants a ratio, it's going to be this. It's going to be 2u, because that's how quick a is going, to u, which is 2 to 1. Okay? What we want to show is that the final speed is also 2 to 1, so that's what we have to work to get. Okay, but the thing is, we don't know the final speed because those are VB and VA. So what are we going to do, buddies? That's right, we're going to do the whole palaver. Let's do it, my lovelies. Here we go. First thing, let's get E out of the way. So let's do it. E is going to equal the V sep over V app again, my lovelies. Okay, E we don't know, so E equals, and the separation speed, we don't know that, V sep. And the approach speed, we do know that. How quick is the gap between these two closing? How quick is the gap between them closing? One's going 2u to the right, one's going 2u to the left. The gap's closing at 3u. 3u, which means the separation speed is equal to 3ue. Cool? Which means VB minus VA is equal to 3ue. Happy days, buddies? Because VB take VA to get the speed that these guys are leaving over there. Cool! Phase 2, conservation of momentum. So here we go. The P before is going to equal the momentum after. Cool. I presume that they're both right. But they're both to the right, but it doesn't make any difference if I get that wrong, so it doesn't make any difference. So here we go. I said right was positive. Now initially then, that means that we're going to have from A, the momentum from A, it's going to be 2u times, or mv it should be, so I'll do m times 2u. Now the other one though, it's going the wrong way, so it's negative. So asserting my sign convention, I don't have to have a negative u, I've got the negative asserted already, and this is going to be 2m times u. Cool? That's the before. Now after, I've got them both in the same direction. I might be right, I might be wrong, but let's see if I am or if I'm not right or wrong. And here's what it's going to be. You're just going to get m times VA, and then you're going to get plus 2m times VB. Cool, cool, cool. This is going to be 2mu. Take away 2mu. Oh dear, the left is 0. On this side, here's what we're going to get. We're going to get mVA plus 2m VB. Cool. Anyone spot anything clever? That's right, buddies. The m's cancel. They're the same m because they're both defined in terms of the same m. One is twice as big as the other, but they're defined in terms of the same m. So here's what we've got. 0 equals VA plus 2VB. Cool. And now we're out of ideas. So what are we going to do? We need to still know what VA and VB are, but we don't want them with regards to each other. We'd like them with regards to the initial u's, because that will cancel out in the end, which is a good thing. So yeah, that's what we're going to do. Well, in this case, here's what I'm going to do. I'm going to say that VA is going to equal, so VA is going to be equal to VB. I should have done it the other way. That's all right, though. VB take away 3UE. Cool. I'm going to pop that into here. And here's what we're going to get. It's going to be 0 equals VB minus 3UE from the VA part plus 2VB. Cool? So here we go. 0 equals 3VB. 3VB minus 3UE, which means that, well, which means that's very good, which means that 3UE equals 3VB, and my golly lovelies, 3 means that VB is equal to UE. How exciting. Cool. How do you get the other one then? How do you get A? Well, all you're going to do to get A then, ooh, I'm running out of space. All you're going to do to get A is you are going to, I'm going to put a highlight on that as well because this is important. Okay. To get A now, all we have to do is pop it back into whatever one. So let's go into, oh, I haven't even numbered them. 1, 2. Let's go into 2 actually, because I think that one might be easier. Well, here's what you're going to get. 0 equals VA plus 2 VB, but VB is UE. Cool? Which means VA is equal to negative 2 UE, which is neat for several reasons. So that's it, boom. Now that's neat for several reasons. So first things first, we can tell we're going to answer the question correctly now. But second thing second, this is negative. What does that mean? That's right, it means that my assumption was wrong, buddies. So do you see how I had VA going toward the right? That's not right. They ricocheted off each other like that. So do you see how I picked the wrong convention, but I got the right answer in the end? It just means that I had it pointed the wrong way. It's going left. Cool? Now here you go. Final speed. Let's just confirm this thing. A to B, A to B. And here's what we've got in terms of our final speeds. The final speed of A is minus 2 UE. But it's the speed, and minus is denoting a direction. So it's 2 UE. I can ditch the minus, because I want about speed, not speed to the left or speed to the right. So it's just 2 UE is its speed. And then the final speed of B was UE. Well, by golly lovelies, 2 to 1, confirmed. Oh yeah, confirmed. Cool. And that's that, buddies. Now, I hope that's okay. That's kind of the hard part. This part's not as bad. I'm running out of space is my only worry. Watch me be really clever here. Or not clever, we'll have to see in a minute. Oh no, it wasn't clever. Oh dear. Oh dear. Oh, I know how to do it. Lasso sort. Okay, watch this. It's going to blow your mind, but it is lasso select all of this malarkey. Oh yeah, look at that, buddies. Oh yeah. Okay, now watch this. Here we go. Oh, get our shrink on. Okay. Boom. Oh, I let go of it though. Oh no, no, oh no. Oh no, oh no, again. I'm wasting time on the online video. Here we go. Quick. We can do this. Okay, there it is, all grouped together. Shrink it up. There we go. Shrink it up. Just leave enough room. Perfect. Pull it down a bit. Beautiful. Okay, there we go. Cool. Look at me. I'm mid-room. Okay, now for part B, buddies, it wants to know about the loss in kinetic energy, okay? Loss in kinetic energy in terms of the variables. So number 2 is actually not as bad as number 1, so I'm just going to block this off just because I still need it, that's all. So here we go. For part 2, 1, 2, the loss in kinetic energy, we'll just consider before and after. The only energy it had was kinetic, so here we go. Energy before is going to equal this. Well, it's a half mv squared for kinetic energy. The A has just got mass m, and the v is 2u squared. That's the first one. Remember, energy is a scalar, not a vector, so we can ditch all negatives and positives. So here we go. This one is a half for B. The mass is 2m, and we've got u squared. So the total energy before is going to be this. 2 squared is 4, half is 2, 2mu squared. Half 2, so this is just plus mu squared. So the total energy before, in the whole system before they collide, is 3mu squared. We would expect the energy after to be less than that because of the coefficient of restitution was not 1, so energy was lost. So here we go, let's do after. After, same deal. Well, energy after, here we go. Energy after, oh, yeah, a shame I'm using A's and B's, and I'm using, this is meaning after, this A. The energy after, here we go. It's going to be for A, it is half m, which was m, and v, which was 2ue squared, plus a half, and b was 2m, and its speed was ue squared after. So the energy after is going to be 4, 2, so that's 2 m u squared e squared. And this guy here is just going to be mu squared e squared. Mu squared e squared, which means that the energy after is going to equal 3mu squared e squared. Cool! So the loss in kinetic energy, buddies, Let's rock out. It's going to be amazing. Delta E like a boss. Oh, that's changing, but oh well. Delta E like a boss. It's had to have more initially, so it's going to be 3mu squared. Take away 3mu squared E squared, which by Jove should be the final answer. But let's be snazzy and let's factorize it. 3m, u squared's common as well. U squared, 1 take e squared. Like a beast. That's the final answer. I hope that that's okay. I hope that this video wasn't ages. It feels like it took ages. But I hope that's it. That's as hard as they go. So you're going to be having no worries at all if you can do that, okay? So that's a hard one. This is a hard one. Important to look at the sign convention with the positives and the negatives. Remembering energy is without a sign. Speed is without a sign. And yeah, velocity is with a sign. Hooray! So we've talked about all of these things. Cool. That's it, buddies. So here's what you're going to do for the remainder of the period, which isn't very long. It's this. I want you to do page 142, question 1 to 16, but just do a mix. When I see you again on Friday, we're going to just do a practice whole day on this. So if you feel like you've been robbed of a chance to practice, don't worry, the practice is coming. I'll do my best to find you those really hard exam questions, and it'll be good when I'm back in school to do the hard exam lesson together. So yeah, that's it from me. Have a lovely day. I'll see you on Friday, which will be amazing. And have a good day. Bye, lovelies!